Good news, everybody. I've been released from my basement, and I'm ready to go with our final lesson on circuits, complex circuits, the circuit with a name designed to inspire. I hope you enjoy. Okay, so here we have our circuit once again. Bulbs A, B, and C clearly labeled up top. Now, what you might notice is I actually cut this a little bit to make this demonstration a little clearer. What we have is, if we come out of the negative side of the battery, so let's watch out, we're dealing with electron current here, not conventional current. But again, it doesn't matter, we're just going the opposite direction. We follow this path through here, up this wire to here. Now, the electrons can't go this way, so they're going to be forced up through this bulb. Just a reminder, it goes through the bottom of the bulb, through the filament, to the brass sheathing, out the brass sheathing to this metal wire here, which drops down here to this point, goes around this to here. This junction, as we learned, we can call it. Now, something important to note, at this point, what we know is that the bulb C is in series with the battery, right? Bulb C is in a direct line with the battery. Or in other words, if I follow a path of charge, the charge has to go through both the battery and the bulb without ever breaking off, because the current can't go here because there's an infinite resistance. Okay? So battery in series with bulb C down this wire to this point. Now we reach a junction, right? The current can either go to the left towards bulb A or up towards bulb B. But if we go up towards bulb B, we see that there's nowhere for the bulb or the charges to reach the other high potential side of the battery. So it's not going to go to B at all. B is basically the same as this part here. Current has no desire to go here. Current will have no desire to go here. So it goes through this wire to here, up through A, through the sheathing, through the wire to the switch, back to the battery. So following again, just quickly, up through here to here, through the bulb C, over to here, here, through A to the switch, back to the battery. Can you tell what kind of circuit this is? Well, current only has one path to take, and so therefore it is a series circuit. If I wanted to draw this with a circuit diagram, it would look kind of like this. Again, out the low end through C, over to A, down, back to the battery. And since these are both the same bulbs, we should expect when I flip this switch, both bulbs illuminate the same amount, and there you have it. Okay, so A and C will both have the same potential difference. The sum of the potential differences, according to series circuits, will be equal to the potential difference of the battery. And they share the same current because, as we know in a series circuit, current can only travel one path. Okay, so there's our circuit. Now, what I'm going to do is I'm going to mix this up a little bit. I'm going to take this little wire here, I'm going to flip my switch, I'm going to place the wire here, and I'm going to go across to A. So now, if we follow that current, the battery is still in line with bulb C or in series with bulb C. I haven't changed anything there. I reach this junction, and now the current does have two opportunities. The current can go through this wire up through A, or it can go up here through B, through this sheathing, pass through. Remember, this part of the brass and this part of the brass are directly connected, so the current that goes through this bulb B doesn't care that A is there, goes straight through, and then through this wire. Okay, so actually, if you think about it, right, if the current is splitting at a junction, passing through and joining back together, we say that's in parallel, right? So let's flip the switch. Let's see what happens. Okay, there you have it. A and B are both illuminated now. We're forcing current to go through that bulb B. That makes sense. That should make sense to us because there's now a potential difference across bulb B, and C is still lighting up. Okay. If we wanted to draw this circuit out, it no longer looks like our series circuit from before. It looks like this here. We're coming out, we're forced to go through C, we go up, we meet a junction, we break off to B and A, recombine here, and come back to the battery like that, to the high potential side. If we're electrons, again, we're not using conventional current. So we're really comparing these two circuits right here. A series circuit at the top, this one, and another circuit here at the bottom, which is some sort of a weird combination, right? Because C is in series with Vs, the source, or the battery, but A and B are in parallel with each other. This is a different kind of circuit. This is a complex circuit. It is neither series nor parallel. if I really wanted to, I actually could take this wire here, and instead of removing it, if I wanted to go back to my simple series circuit, I can just do that, right? I've now disconnected B from the circuit, or I can like that to go back to the second circuit. So this little wire here is basically acting like a switch. So if I wanted to draw my two circuits, these two right here, as one circuit, I could draw it like this. Okay. Here, right, I come out of the loci, just like here. I'm forced through C. Whether this switch is opened or closed, the current has to go through C. Now when the switch is open, this situation here, the current reaches this junction, doesn't want to go through B, so there's a dead end there, no different than this right here, and so it's forced through A. And then we have a simple series circuit with A and C. When I close that switch, when the current reaches this point here, it has to choose which path to go, so there's a junction. It will go like this, pass through both bulbs, meet up here, and go out the other end. You can also look at, if this is in parallel, right, the current passes through C, breaks up here, the current breaks up through A and B and splits. This explains why A and B are dimmer than C, right? Because C is receiving that total current out of the battery. All of it goes through here. Current has to split up. That's Kirchhoff's laws, or the conservation of charge. Splits up, and so A and B get less current and therefore dimmer. But now, I think that's easy to address. What's harder to address is this. Here's my first circuit. I want you to just look at bulb C. When I close that switch, what happens to bulb C? Ready? Watch it, watch it. It gets brighter, doesn't it? Well, that's going to be our aim. Why does bulb C get brighter when the switch is closed? So let's have that discussion. All right, so here's our aim. And when we talk about bulb C getting brighter, what are we talking about? Well, we're talking about power, aren't we? We're looking to address the issue of why is bulb C's power getting larger when I close that switch? And now when we're talking about power, we have to consider what equations we're talking about. P is equal to V squared over R. And it's also equal to I squared times R. And it's also equal to IV, right? So those are my power equations, and that's ultimately what I need to get at in order to answer my question. So to do that, what I want to do is I want to make a table to look at the two situations. One situation is when my switch is opened, and one situation is when my switch is closed. And what I'm going to do is when I talk about the switch closed, I'm going to put a little prime on any variable that would change when I close the switch. That way we can make a comparison between the two. Okay, so the left side column here is this circuit, and the right side column is this circuit, just to keep track. And that's just as easily represented by talking about this switch opening or closing. All right, so what do we want to start with? I'd like to start by discussing the potential difference of these two situations. Knowing that the potential difference of the source is the same in both cases. Well, knowing that the potential difference of the source is the same in both cases allows us to say that when the switch is open, so when it's just a series circuit, Vs is equal to I total times Req. Right? Vs is equal to I total Req. Always going to be true just by Ohm's law. When the switch is closed, I can say that Vs is equal to I total times Req. But here I need to include those primes. So I'll put a prime on the current total and a prime on the Req because we're not sure what's going to happen there. But we know the battery didn't change, so Vs will not change, so I'm not going to bother priming it. That will tell us that this source voltage is the same as this source voltage, which when I close this switch, I'm not changing my battery, so those two should not change. Okay, so that's established. Now, I'm going to kind of put like a dashed line here because what I'm going to say next is just some observations or some things we can say about this circuit. It's not necessarily that it's important to the current conversation. One, when the switch is open, we know that the potential difference across B is equal to 0. because there's no current passing through. Current is 0, Ohm's law, V equals IR, tells us that the potential difference must be 0. The next thing we can say, and this is a really important one, is that the source voltage when the switch is open is equal to VC plus VA, right? Because there's no potential difference over V, and so if I put a voltmeter here and a voltmeter here in a series circuit, it should add up to the total voltage. Now what about when the switch is closed? Well, when the switch is closed, I know from my parallel rules that the potential difference of A prime has to be equal to the potential difference of B prime. Remember that prime is the switch closed. Those two must be equal because they're in parallel. They must be equal to each other. What else do I know? Well, I know that the voltage of the source, which again is the same as it was when the switch was open, is equal to VC. Now it's prime, because I don't know if VC changed. And since it got brighter, we can kind of assume it did, but we don't know by how much. VC prime, and then, well, let's see. A and B have the same value. So do I do VC plus VA prime plus VB prime? Is that what I'm going to do here? Well, if I had a regular parallel circuit, ignore C. Let's just say we have this circuit here. Would I say that Vs is equal to Vb plus Va? No, that would be incorrect, right? Because I know that these two both share this source voltage. So when I do this, I actually double count. So that's wrong. I can't do that. But what I can say is that if the source voltage is Vc prime plus Va prime, it is also equal to Vc prime plus Vb prime. Because again, Va equals Vb prime. Okay, that's an important detail to see. Now, we got to this equation at the start. We just talked a bit about the relationships between the voltage of the three bulbs in the situation. But if you look at this, it really isn't giving us enough information to answer the game, why it got brighter. Okay. So in order to do that, what we're going to explore next is REQ, the equivalent resistance of these two circuits. Well, when the switch is open, I have my basic series circuit. We know that our series circuit rules are that the total resistance of the circuit is the sum of the individual resistances. So this will be RA plus RC. I forgot to give you values here, so what I'm going to say is that if I put it over here, RA equals RB equals RC, and I want to say that each of those is equal to 3 ohms, just to make things easy for us. And then we can through here. Right? And then I'm going to say that Vs is equal to, I believe I said 12 volts in my thing. Yep, 12 volts. So here I'll have 3 ohms plus 3 ohms, or 6 ohms. Easy. So that's my resistance here. Now, let's switch over to the closed circuit. What is REQ prime? Well, this is harder, right? Because in this case, I don't have, going back, I'm going to flip this up like this, so it's a little bit easier for me to work with, or maybe I can do this one. There we go. Okay, so here, I don't have a parallel circuit, I don't have a series circuit, so what rules do I use? Well, I need to combine my equivalent resistances as a complex circuit. And a complex circuit is a circuit where resistors are in series and parallel. And now, one thing that I really like about doing complex circuits and teaching it is that what am I trying to say here? The rules that you learned before for series and parallel still apply. We're just going to like dissect this circuit and apply those rules at specific points. What I mean by that is if we take a look at, if I take a look at resistors A and B, I want to grab a red marker, I took the black marker. If I look at resistors A and B, those two are clearly in parallel with each other, right? So I can say that I can say that A is in parallel with B. They're in parallel with each other, which means that if I want to get the equivalent resistance of these two, it's sort of like having a bulb here that I'll call AB. So A and B no longer exist, and I call them instead AB. Well, what's the resistance of AB? Well, it's two bulbs in series, or two resistors in executing in parallel. And so I can say 1 over RAB is equal to 1 over A plus 1 over RB. I'm just applying my rules of parallel circuits here. And so if you just do a little bit of algebra, you get that RAB is equal to RA RB over RA plus RB. And a little algebra again, we get that this is RAB equals 1.5 ohms. Okay, so that's the resistance of this portion here. Well, now, if I look at bulb AB and bulb C, I see that these are actually in series with each other. So my next part will be to say that AB is in series with C. Okay, so AB in series with C. And so my REQ, which I can call RABC if I choose, is RAB plus RC, my series rules. That's 1.5 ohms. I can't believe I have enough space here. This is great. Plus 3 ohms, or 4.5 ohms. So we just found the equivalent resistance of my complex circuit here. Right? So we have the equivalent resistance of the complex, and we have the resistance of the series. Okay? So that found us our resistance of the circuit, but the resistance is not actually enough to determine the power loss at this point, because we don't know anything about the potential. If we look back here, we know something about the resistance, but that's not enough because we don't know enough about the potential and we don't know anything about the current. So to talk about that, let's continue our little table here. Okay, so here I have open, closed, and get a little lazy, and let's talk now about the current of the circuit. Well, back to this equation. I can say that I total is equal to Vs over Req. Well, that's equal to, I told you 12 volts over, what did I get? 6 ohms or 2 amps. Perfect, we solved it. Now in the closed circuit, same thing. I can say I total prime is equal to Vs, which was the same in both cases, over Req prime. And I should make that prime, shouldn't I? Because the equivalent resistance changed, even though the individual resistors did not. Okay, so what is this? This is 12 volts over 4.5 ohms, which comes out to, what's that? 2.7 amps approximately. All right, so great. But what is this current? What is that current? Go back here. That's the current out of the battery, isn't it? So if I took an ammeter and I place an ammeter right here, or I put my little paper on, right? If I put my ammeter right there, that's the current through that portion. Or I could say it's the current through C. So if I then put this dashed line, when we look at the open circuit, I can say that the I total is equal to IC, which is equal to IA, because it's a series circuit and we know the current is the same everywhere. Whereas for the complex circuit, I can say that I total prime is equal to IC prime. That's still true, isn't it? Because when this switch is closed, all the current out of the battery will pass through C, but then it splits up. So I can say then that this total current, which splits up at this junction, is equal to IA prime plus IB prime. Okay. So just a useful bit of information about that type of circuit. I'll return this right here. Still haven't gotten to the power part though, right? So let's continue our table downwards and talk about the power. Well, we have a couple equations here, right? We can use V squared over R, I squared R, or IV. What do we want to choose? Well, if we think about it, right now we know information about I, we solve for it. We know R, and so we can solve for these powers, for C. So I can say PC here is equal to IC squared RC, which is equal to 2 amps squared times 3, let me make that clear, 3 ohms right there. And that should come out to be 12 watts. Here, I can say that PC prime is equal to IC prime squared times RC. RC doesn't change. So this will be 2.7 amps squared times 3 ohms. So this is about 22 watts. So here we can see that PC was less than PC prime. Proof of, or even an answer to our aim of why does bulb C get brighter when the switch is closed? Well, the power prime is clearly greater when the switch is closed for C than it was when it was open. So we just proved that. I also, I didn't have to do any of these calculations. I could have just said that, IC is less than IC prime, so therefore PC is less than PC prime. Could have done it that easily. Great. All right, now, let's pull my setup back up here. We've answered the aim, but I still have one more question about what happens when the switch is flipped. I'll turn this on, hopefully everything works. Of course not, it never will. Okay, so there I have it. Watch C, I'll flip that switch. Boom, gets brighter, telling us that the power of C increased. The current increased, right? If I had that little ammeter here, we'd read a large value and then a smaller value. But now, instead of looking at C increasing, think about B. Well, clearly B will get brighter when I close the switch, because before there was no current passing through, now there is. But look at A. When I close the switch, what happens to A? A gets dimmer, doesn't it? Right? Again. Brighter, dimmer, brighter, dimmer, brighter, dimmer. Okay? So A actually gets dimmer when I hook up my switch, and let's look at why that is. So if we look at the question, why does A get dimmer when the switch is closed? Well, to do that, what we're going to do is we're going to go back to this equation here. These guys. Well, vacuum I open and closed. Open, closed. I know that Vs here is equal to Vc plus Va. Well, I actually have enough information to solve this now, because I know what Vs is. Vc is going to be Ic times Rc plus Va. This is 12 volts equals, well, did we find out what Ic was? We did, didn't we? It was 2.7 amps times 3 ohms plus Va. We have everything here. Va, we can solve, and it comes out to be, oh, that's not 2.7, that's 2. That comes out to be 6 volts. But when it's closed, well, actually, when it's closed, it's the same equation, right? Vc prime plus Va prime. But now I have Vs is equal to IC prime RC prime plus VA prime. 12 volts equals 2.7 amps, do it right this time, times 3 ohms, that's squared, no, it's not, excuse me, plus VA prime. And so if we do that, we find that VA prime is equal to 3.9 volts. Cool. So there we have it. VA's potential gets smaller when we put it into the complex circuit. All right. Now you may be looking at this and be like, okay, why are we using? Why are we using this equation now, but before we used this equation? Well, the answer is we actually could have done it the other way. If we wanted to, we could have found what the change in current for A was, and we would have found the same result because the resistance didn't change. And so as we can see, V and I are both in the numerator, so if one decreases, the other one will also decrease as long as R of the resistor itself does not change. Okay, I just chose to go with V this time. By that same logic, we can tell that V had to decrease, right, the potential difference of, actually I can look at it this way, which will be even nicer. If we look here, A got smaller, right, which means that C had to get bigger, because this relationship's still true. If A gets smaller, here, C has to get bigger to keep Vs the same. That's a nice little application. All right. Continuing on. Here I have a sample problem for us to look at. Okay, so here is my circuit, and what we have are the same 3 bulbs and potential source, and we're looking for the current read by the ammeter. Okay, so in order to do this, we're going to start by looking at, as always, our oh so important Ohm's law. Vs equals I total Req. We know what Vs is, which is great. All we need to do now is determine what Req is. Well, to find out what Req is, we're going to do the same deal we did before. We're going to group together certain resistors. So here, A and B are in series with each other. So I'm going to start by finding what RAB is. Well, that's RA plus RB, which is 6 ohms. Cool. So the way I actually do this is I redraw my circuit. I say, okay, now I have a circuit that looks like this, right, where this is AB and this is C. And I say, well, now AB is in parallel with C, right? So I want to say that 1 over RABC is equal to, which, let's also input that this is REQ, right? It's equal to 1 over RAB plus 1 over RC, which is equal to 1 over 6 ohms plus 1 over, that's not a 3 ohms. Okay, do the math, and you get that REQ is equal to 2 ohms. So now we have REQ. Vs is given up here as 12 volts. Go over to here. My I total is equal to Vs over Req, which is going to be equal to 12 volts over 2 ohms, or 6 amps. Cool. So that 6 amps is the measurement that that ammeter would give you in this circuit. Notice, it's a very different circuit from the previous one. We're still getting the same current, just by how we happen to have arranged the circuit itself. Now, what if the question asked, what's the current through RC? What is the current through RC here? Well, notice this battery is in parallel. This battery is in parallel with A and B together. And it's also in parallel with C, right? C is, if we drew a line from battery, it directly connects to the C on the high potential and the low potential, which means that VC is equal to Vs. They're in parallel with each other. Okay? Or excuse me, the battery is in series with C, but C is in parallel with the whole circuit. So then I can say that VC is equal to current through C times RC. Well, from that, C is equal to VC over RC, which is 12 volts over 3 ohms, or 12 over 3, 4 amps. Okay, 4 amps goes through C. Now, what about the current through A? What about the current through RA? There are two ways to approach this. Okay? Method one, I'll put on this side, is saying, okay, well, VS is equal to VAB. If I put a voltmeter here, I would get the same potential difference as VS because this and this are connected directly to the battery. So then I can say, well, VAB is equal to Ohm's law. The current through AB, and A and B are in series, so they have the same current. So I can just call it IA. Or IB, it doesn't make any difference at all. Times R, well, I'm dealing with A and B, so AB. What does this mean? Well, they're in series with each other, so I can say that VAB is equal to IA times RA plus RB. And you may be thinking like, okay, how did I know that? Why? I'm just talking about A, so why do I include B in that? Well, imagine if I put a third resistor C here. Wouldn't that make the current even lower through A? So I can't just consider A. I need to consider what else is affecting the current in the same branch as A. Okay, so I have this equation here. This is 12 volts equals our unknown times this becomes 6 ohms. Well then, IA is equal to 3 amps. Done. This is also equal to IB, right? Because they're in series with each other. The next way is by thinking about the junction. Well, I know at a junction, the incoming current is different color. The I total breaks into two smaller i's, right? I can say IC, and then I can say IAB. So the current breaks into those two. Therefore, I total must be equal to IAB plus IC. And as I said before, I can say this is the same as IA plus IC, or IB plus IC, no difference at all. What is I total? We found that. It's 6 amps. It's equal to IA plus, did I do something wrong? Plus IC, which is, I have here is 4 amps. So IA is equal to 2 amps. Well, now I have a problem. I have an inconsistency here. And this is a genuine mistake, but I do know which one is right. I know which one is right because if I think about this junction here has twice the resistance of this junction here, doesn't it? So twice the resistance as this one, but the same potential difference, which means that the current through C needs to be double the current through A and B. Well, that's consistent with this row here. So now my question is, what did I do here? I divided terribly, right? 12 divided by 6, I'm glad that's the only mistake I made, so that should be 2 amps. Okay, that's why it's always good to check over your work. Cool, so that is it for complex circuits. On Google Classroom, you'll find that I gave a sheet that provides you with a guide as to how to solve complex series and parallel circuit questions, and you have a Castle Learning assignment up that's due Tuesday night. So go ahead, get to those. I hope to see you during the lesson recap, and I hope that you found this clear and not too confusing.